Right, so today's class we're looking at topic 3, mass and forces. All right, so mass, this is the measure of the amount of matter in an object. So mass stays the same no matter where the object is located. So if you were on Earth or if you were on the moon, your mass would stay the same. Mass will change if you gain matter, like if you eat a large meal, or if you lose matter, like burning energy through exercise. Right? So mass can change, but it does stay the same. It doesn't matter where you are, because next we'll talk about weight. Weight will depend on gravity. So here, kilogram, that's the primary measurement of mass in the SI system, the metric system, which is used in Canada and in most of the world. It's equal to 1,000 grams, and 1 kilogram is the primary standard that is used for mass. All right, so here is just showing that metric system here. So kilo, hecto, deca, then we have our gram, because we're talking about grams. So here's our gram. Then we'd have decigram, centigram, milligram. This is a balance. A balance is a device that's used to measure mass. The standard kilogram has about the same mass as 1 liter of water, or another liquid like milk or juice. So next we're going to talk about weight. Weight is the force of gravity exerted on a mass. So the weight can change if you are on the moon compared to on Earth, and that's because of the different forces of gravity. So weight is a force. So here weight is shown as equal to the mass multiplied by that gravitational strength. All right, so that becomes mass is in kilograms, and then that gravitational field strength is in newtons times kilograms. Okay, and then weight is measured in newtons. So what is a force? It's a push or a pull or anything that causes a change in the motion of an object. It is measured in newtons. So just comparing some forces of different sizes here. It's about 1 Newton force to lift a flashlight battery, a D cell. Here it's about 10 newtons, the force that can lift a 1 liter carton of milk, and here about 200 newtons, the force of a hard thrown baseball hitting your hand. All right, a little bit about Isaac Newton. He was the first to start investigating weight in the 17th century. So basically the story is that he was sitting under an apple tree and he began to wonder why the apples were always falling down towards Earth. Why didn't they fall up into the sky or just float in midair? So he realized that there must be some sort of force, and that there is a force between any two objects anywhere in the universe that tries to pull them together. So he used his mathematical skills, analyzed the size of the force, and then he called it gravity. So what he found was that the gravitational force between two objects, it depends on the masses of the objects as well as the distance between them. Okay, so gravitational force, it's the force that's exerted by gravity on an object. It's a force, it's measured in newtons. There's a gravitational force about 10 newtons between 1 kilogram mass and Earth. So we would therefore say that that mass has a weight of 10 newtons. The actual number is 9.8 newtons. We just rounded up to 10 newtons just for calculations. So gravitational force, it depends on the distance between objects. So an object's weight changes depending on where it is. So if you're in an airplane high up in the sky, or if you're on a high mountain, you're farther from the center of Earth, so your weight is a little bit less. Okay, but keep in mind your mass doesn't change. Your mass stays the same. Gravitational force depends on the mass of an object, like we saw in the formula. So if you went on the moon, your weight would be about 1/6 what it is on Earth. And that's because the moon's smaller mass, it exerts less gravitational force than Earth's mass. All right, so your weight would be less on the moon, but your mass would still be the same. Here we're just looking at a force diagram. This is a diagram. It's a simple picture. It uses arrows to show the strength and direction of one or more forces. So here we're looking at an elevator. So an elevator here is standing still. This is our force diagram here shown with the arrows. Okay, so the force, this is the elevator represented by the circle. The force of the cable pulling it up, it's the same as the force of gravity pulling down. So the sizes and lengths of the arrows are the same. In this picture, we're looking at the elevator is beginning to rise. So you'll notice the arrow is longer, pointing upwards. The circle represents the elevator, and then we have a shorter arrow pointing downwards. Okay, so that circle, or you can use a rectangle, it stands for the object on which the forces act. And then each force is shown by an arrow. The length of the arrow shows the size of the force. Okay, a longer arrow means a larger force. The direction of the arrow will show the direction of the force. All right, so the arrow, it's usually drawn pointing away from the place where the force is acting. So kind of like a rope pulling on an object. Okay, so that's what a force diagram looks like. So we have a couple videos to see here comparing gravity, weight, and mass. I'm just going to pause here.